these two equations are really important foundational equations to figure out what's going on with Newton's cradle. So if we have Newton's cradle here, right, we're going to have each one of these, we're going to call this one ball A, ball B, and we'll call it C, and then we'll call it D. All right, so what we want to do is we want to pull ball A back here in such a way that we make an angle. We make an angle right here, and that's going to cause ball D to fling off and cause an angle here. We'll call this angle theta. In a world where the energy in is equal to the energy out, theta and theta prime are equal to each other. And we're going to have velocity in A direction, velocity A, and then we're going to have velocity prime D here. Okay, so I'll show you what this prime means in a moment. Because initially velocity D is going to be 0. So what we want to do is we want to equate this theta with this theta, and then we want to equate this velocity with this velocity. Okay, so that's our goal. Our goal is to bring these together. How does this relate to this, and how does this relate to that? Okay, so to start out with, to get to that point, we need to start out with these two equations. And what are these two equations? These two equations, the top equation is basically your momentum equals momentum before is going to be equal to momentum after. So let's say, what does that mean? So if we have a mass A and we have a mass B and we have a velocity A going in this direction and we have a velocity B going in this direction, after impact we're going to have a mass A and you're going to have a velocity A and we're going to have a mass B and you're going to have a velocity B. And to keep those two separate, we're going to make this prime. All right, so this velocity B, we're going to say because A had greater velocity or greater mass, it's going to have B in this direction. Simply for this case. All right, so what does that mean? That means that this momentum is going to be equal to this momentum. We'll call this momentum prime. So that momentum is equal to mass times velocity. So we know that mass A times velocity A plus mass B times velocity B, don't forget the negative because it's going in a different direction, is going to be equal to velocity prime A. I'm sorry, let's go with the mass first. This makes it a little bit more easy. Just makes it easier. Mass A times velocity prime A plus mass B times velocity prime B. All right, so now you understand why I was talking about D, velocity D prime, because it's after the impact. All right, it's before impact, after impact. So mathematicians and physicists like to think, hey, in the case of the Newton's cradle, all the masses are the same, so basically they all cancel out, right? We're going to assume that every one of those balls that have the exact same mass. I mean, do they have the exact same mass? Probably not, but they're so close in the macro world that we're not going to worry about it. So we're going to say that mass A equals mass B, so they all cancel. So what we're left with is velocity A plus velocity B is going to be equal to velocity prime A plus velocity prime B. All right, so mathematicians and physicists like to have numbers. So we're going to call this number, we're going to say, we're going to take this side and divide it by this side and make it a number out of it. So take this side divided by this side. So we're going to have this velocity, and we're going to take the negative of it because we want to know the difference. So we're going to take the negative of velocity A minus velocity B divided by velocity A minus velocity B. All right, so this equation, and my prime is over here, this equation is very important. It's a nice little equation. Don't get it confused with Euler's E. They just happen to, I think it's called the resolution E, resolution equation. It is a good equation. I think it goes from 0 to 1, like an E equals 1. I think that both of the the masses are separate at the quickest possible way they can separate. And then E equals 0. The two masses stick together. So it's elastic and inelastic. So when E equals 0, they stick together. And then everything in between, like E equals 0.9, right? So it's a little bit, the rate that they separate's a little bit slower. And then when E is equal to, it doesn't matter if it's negative 0.24, right? They separate, I mean, up here they separate faster, down here they separate slower. So more or less they're stuck together here, they fly away from, they fly apart. So it's a very interesting, and it's a good number. It's a very interesting way of understanding how these things stick together or fly apart. This number right here. It gives you an indication of what's going on. All right, so in our world, in this world right here, we have two equations, two unknowns. So we need to get rid of one of these. Yeah, get rid of one of these equations and make it just one solid equation. So how do we do that? Probably the easiest way to do that is to solve this thing for velocity prime b and put it in here, and then end up solving for velocity a. So let's see how we can do that. So E is going to be equal to negative velocity prime a minus velocity prime b, right, divided by VA minus VB. All right, so we can take this thing and multiply it by both sides. So you're going to have E times VA minus VB, and that's going to be equal to V prime A, the negative of V prime A, plus the velocity prime B. Okay, so I just distributed that negative. All right, so since we distributed a negative, we distributed the E, so we have E equals VA, right, minus E VB, right, negative, is going to be equal to minus V prime A plus VB prime. Well, we just add V prime A to both sides. We're going to get E VA minus E VB plus V prime A, and that's going to be equal to V prime B. All right, so if we take this thing and we stick it back into here, we should be able to resolve both equations, and we can do that. Let's take a picture. All right, so how can we do that? So let's stick that we just got done with and stick that into our equation. So we're going to get MA VA plus MB negative V is going to equal to MA V prime A plus MB. Now we just solve for velocity prime B. We can stick that in there, which is E VA minus E VB plus V prime A. All right, so let's distribute the MB. We'll distribute this MB into each part. All right, I'll say it. So we got MA VA plus MB times VB is going to be equal to MA, a little repetitive, MA plus MB. So let's put the E first. This looks nicer. MB VA minus E MB VB plus MB V prime A. All right, so now we're left with this thing. What do we do with this? Well, we have some like terms here. We got VAs, We have the VBs, and then we have the VA. Let's put these two together. So we have MA, VA, and here's our E, MB, VA. So this would be minus E, MB, VA. Right? So these two are gone. Let's put these together. So this would be plus MB, VB. And then this thing right here. So this would be plus E, MB, VB. And all of this is going to be equal to what? MAV, MA, V prime A, plus MB, V prime B. V prime A, sorry. This would not be a B, this is A. All right, so now we can pull out the VA, we can pull that out. We can distribute the VBs and the MB, we can distribute the V prime A. Let's do that. So we get VA times MA, what would that be? MA, VA would be 1 minus. Would that be 1 minus? Oh no, it's MA, MB. So we have MA, I'm sorry, MA minus E, MB. Right? VA times that, right. Okay, good. And then we're going to distribute out the what? MB, VB. Distribute that out, so you get what? 1 plus E. Does that make sense? Yes, it does, right? And then that's going to be equal to what? V prime A. And then MA plus MB. Oh, good. So now we can solve for VA. Let's solve for VA. So we get VA, V prime A, is going to be equal to all this stuff. So this would be VA times MA minus E, MB, plus MB, VB, right? 1 plus E, whoops, sorry. 1 plus E, not plus 1E. 1 plus E. Don't forget, this is not Euler's equation, or not Euler's E. And then we're going to divide that by this thing right here. MA plus MB. Whoa, we got another equation. Actually, a very good equation. It's an equation that we can use because now we know the velocity of the prime A. So we know the velocity of A after the impact. So let's keep that. I mean, that's one that I would not. I'll let you take a picture. Let's keep that, and because that's going to be a very important equation when we start looking into this and what our goal is. Hey, so we found VA, V prime A, but we want to find V prime D, V prime D. But anyway, let's put this up here and just for V prime A is going to be equal to VA, right? MA times MA minus E, MB, right? Plus MB, VB, times 1 plus E, all divided by MA plus MB. This is a very important equation. We're going to be using this equation. You can do the same thing. You could play the same trick to find the velocity prime B, right? So what you do with that is you would solve for velocity prime A and then try to solve for velocity B, right? And when you do this, when you do the algebra, it actually comes out to be. In fact, I'm not going to do the algebra. I'm going to let you do the algebra. So V prime B is going to be equal to 1 plus E times MA VA minus MB minus E ma times vb divided by ma plus mb. You play the same game to get to this one. You play the very same game, which is going to be good. So let's go back to our Newton's Cradle and start figuring out what heights are and some other velocities are. So let's go back to Newton's Cradle and think about this. So here it is, our Newton's Cradle thing is going on like this. So we got this and A and B and C and D, right? So when we pull this back, here's A, right? And this is A, this is B, this is C and D. And it's going to create a angle here when we pull this back, and it's going to create an angle over here. We'll call that prime. It's going to have a velocity over here, velocity A, and then this will be velocity prime D over here. Let's figure out how high, what this h is, how this h is related to L. So our L goes from here to here. So this is L. All right, so let's figure out how we can do this. So if we, of course, we're going to use trigonometry, and let's just say here's our theta. We'll call this side y. This is L, right? So the sine of theta is going to be what? Opposite over hypotenuse, y over L. So that y is going to end up equal to what? L sine theta? Okay, that makes sense. All right, so how is y related to h? Well, when h is all the way down here, right? So when we have this all the way down here, this will be what? Y is somewhere in here, so this is y and h, right? So if we think about h, what is h equal to? Well, h is going to be what? H is going to be L minus y, since this is L. So h is going to be what? L minus y, right? So h is going to be equal to, we know L, and we know y, so we know that L minus L sine theta is going to be that. So wait a minute, h is going to be equal to L 1 minus sine theta. Whoa, we got that one done. We found out what h is. We found out how h is related to L and how it's related to sine. So this is actually multiplied. So now we know h. So we know the height is going to be what? L times 1 minus sine theta. All right, so we know h. What else can we figure out? Can we figure out the velocity? Sure, why not? Let's look at the velocity. If we pull ball A back, right, it's going to drop. It's going to drop through this h. It's going to drop, so what does that mean? That means it's going to be a velocity final squared is equal to velocity initial squared plus what? 2gh, right? Well, we know this is 0 because when we hold it here, it's 0. So let's look at velocity final. So our velocity final is going to be what? 2gh square root, right? Well, we know h. H is over here. So velocity final, our velocity final is what? 2 times g times L times 1 minus sine theta square root. Hey, we found a velocity. We found our velocity of the ball of A. So basically, it's VA. We found the velocity or VA final. So right, because it's the velocity at which ball B is going to feel ball A. All right, so let's put that over there just for fun. Velocity is equal to 2g times L times 1 minus sine theta. Now, because we live in this world where our energy in this case is going to be 0, because we're going to say that there's no resistance going on, there's no air resistance, the ball's out of alignment, all that kind of good stuff. We're just going to say that this is going to be equal to that. All right, so let's go with that. Let's just stay with that. All right, so if all the masses here are the same, right? If all the masses here are the same, let's see if we can find out what V prime A is. If all these are the same, let's look at this. So V prime A is going to be equal to VA times ma minus e mb, right? Plus, well, in fact, let's look at velocity b. Let's forget velocity a, because we already know that. We already know velocity a. Let's look at velocity b. So velocity prime b is going to be equal to 1 plus e times ma va, which we already know that, minus mb mb times e ma. Let me multiply that times velocity b divided by what? A ma plus mb. That's this thing right here. This is all I do is transfer it over here. But when we think about this, when this ball comes down here, initially, velocity initial of b, initially, it's going to be 0, right? So the velocity of b initially, before the impact, is going to be 0. So this thing here is 0, right? So that makes this whole thing 0. But now we have velocity prime b is going to be equal to what? 1 plus e. All the m's are the same, so these all cancel. M plus v, or 1 plus e times what? va divided by 2, because m plus m, 2 m's. So we got velocity b is equal to 1 plus e divided by 2 times va. How about that? So now we know after impact. What velocity b will be. If we know e and if we know va, we can figure that out. All right, so let's look at velocity prime c, right? And that's going to be equal to what? 1 plus e divided by 2 times what? Velocity b? Velocity prime b, because that velocity prime b is what it's going to feel. Well, isn't velocity prime b just this thing? So that velocity prime c, right, is going to be equal to 1 plus e divided by 2 times 1 plus e divided by 2, right, times va. Well, that's just v prime c is equal to 1 plus e divided by 2 squared times va. Hey, we just found out that va and how v prime c is related. Well, let's go to d. Let's see what happens in d. So we know c, well, velocity, we're going to play the same game. Velocity prime d is going to be equal to what? 1 plus e divided by 2 times what? Velocity prime c? Well, that's this thing, right? So velocity prime, this would be d. Velocity prime d is going to be equal to what? 1 plus e divided by 2 cubed va. Hey, we just found out how velocity d and velocity e are related. And they're related to this thing e, really. The cube of whatever this thing e is. That's interesting. It's a cube. So in other words, it's a cube for each one of these pieces, right? So there's 3 of these balls that are giving it part of its whatever it's going to get. You know what I mean? Whatever's gone on in here is going to make this. It's going to determine this velocity. No matter what you make velocity a, this thing's going to determine more or less. Those 2 things are going to determine this velocity. That's a very interesting thing. I like cubes, so we're going to put that over here. So velocity d, right, prime is going to be equal to 1 plus e divided by 2 cubed, right, times the va. Whoa. That's just kind of like mind-blowing. Okay, so that's what we get from that. Let's press on. See what else we got. So we just related our velocity here, or our velocity a, and our velocity d. And we related it right here. So now we need to find out how these 2 are related. how these two can be related to one another. We found out how these are related. Now we can find out how these are related. Well, let's see. If we think about this in terms of energy, it becomes a different kind of world. Let's think about this in terms of potential energies and kinetic energies. So I'll get rid of some of this stuff. And look about. Let's think about this as in, this would be a potential energy up here. This would be our initial. The kinetic energy of B down here, initial, that's going to be 0, right? Because it's not moving. And then we're going to have a kinetic energy of D, initial, because it is moving. I mean, once D gets hit, it's going to have a velocity to it. And let's just look over here at the potential energy over here of the final. We're not interested in this. We're just going to say there is a potential energy final. But we're not interested. We're only interested in the initial, right? So let's look at this initial. So we would have potential energy initial is going to be equal to kinetic energy final. All right? So how does that work? So we would say potential energy is what? mgh is equal to 1/2 mv squared. Well, okay. Well, here's h. We kind of know h. But what velocity are we talking about? Well, we're talking about the velocity of what? Velocity initial d. All right, so let's say. So we got mg. H is this thing right here. So this is L times 1 minus sine theta is going to be equal to 1/2. Well, the m's are going to cancel. So we don't even have to worry about it. The m's are going to cancel. So our velocity d, we already know that. That's this thing right here. It's our velocity d. We're going to, because it's the kinetic energy of our velocity d. So we know that already. So that's 1 plus e divided by 2 cubed. But don't forget, we got to square it. Times what? Velocity a squared? Whoa. Okay. So this is kind of weird, but I think it will work. So this would be GL times 1 minus sine theta, right, is going to be equal to 1/2. Well, let's look at VA. We can think of VA as being what? This thing right here? Well, sure, we can. So we're going to square it. So we have 1 plus E divided by 2. Now this becomes to the 6th, right? And then we're going to square this thing, which comes to be 2G, right, times L. And then that's going to be 1 minus sine theta. All right, I'm running out of board. All right, so I think you can see what's going to happen here. So the 2's are going to cancel. The GL's are going to cancel. And you're going to be left with 1 minus sine theta is going to be equal to 1 plus E divided by 2 raised to the 6th. All right, times 1 minus sine theta. Now, here's the important part. What are these sines and what are these thetas? Well, in this case, we're looking at the potentials. So our potential could be this potential here. This, because of this being equal to 0, right? These two are equal. So we could say, hey, this is going to be our sine prime, and then this will just be our sine this is the sign that we're looking for, and this is the sign that we know. This is the sign that we pull the thing back with. All right? It's a little tricky, but it does work. So what we're going to end up with is this. We're going to have a, let's solve this thing. So we get negative sine prime is going to be equal to what? We got to subtract 1 from both sides. So this would be 1 plus E divided by 2 raised to the 6th, 1 minus sine theta, right? This whole thing would be what? Subtracted by 1. Well, we got this negative thing, so we want to get rid of that. So it'd be sine prime is going to be equal to what? 1 plus E divided by 2 raised to the 6th. Oh, wait a minute. Let's make it easier. this becomes a positive, so this would be 1 minus 1 plus e divided by 2 raised to the 6th. There we go. That makes much more sense. Plus sine theta. Make our theta look cute. Sine. Hey, this is an important thing. So now we related the two signs together. It's a little tricky up here to say, hey, this sign equals that sign. And then, but it is a little tricky, but it does work. So this really is our equation that relates both of our thetas. They both are related this way. So I'm running out of room here. I need a bigger board. All right, so let's make this right here, and then we'll say that sine theta prime is equal to 1 minus 1 plus e divided by 2 raised to the 6th, and then 1 plus sine theta. Whoa, okay. These are all the equations you're going to need. These are all the equations you're going to need to figure out Newton's cradle. What? Yeah, it's true. These are all the equations you're going to need to figure out Newton's cradle. Now, it gets a little complicated here. I think what I should do, rather than go on, is make another video. And this is the next video. The next video, I'll call it Newton's Cradle Part 2, right? We'll call this one Part 1 and Part 2. But in Part 2, what we'll do is we'll look at the Newton's Cradle thing going on here, right? And what we'll do is we'll pull this back, we'll pull A back, and then we'll get a D over here. Right, so this would be theta, this would be theta prime. What we're going to do is we're going to pull A back and let it drop, all right? And then what we'll find is that our velocity A, right, and velocity prime D, so velocity after the hit, prime D, so this thing right here is as it flies off here, it'll be velocity prime D. Our velocity A is coming down here. So what we'll find is that velocity prime D will be like about 10% less than VA. So it'll be like 10% less than this. So you're losing 10%. So we take a radar gun or whatever we use, we know this balls, we know the height and all that kind of good stuff, and we'll know all the velocities and all that kind of good stuff. And after we find out what this velocity is, we find out that this velocity right here, this velocity D, through the fact that there is resistance and that the balls aren't completely lined up and all the other reasons why you have less energy, we find out that velocity D is actually 10% less than velocity A, right? And that's going to be actually what that's going to come down to is this thing here, this 1 plus E divided by 2 raised to the 3 or 6 or whatever. This thing here is going to be what? 0.90? Because you're going to lose, this is going to be multiplied. Okay, I might as well just keep on going, right? I might as well not go into the second video. So this thing here, so velocity prime D is going to be equal to 1 plus E divided by 2 cubed, right? VA, right? So this thing here is what is causing VD to slow down, V prime D to slow down, whatever's going on in here. So this thing, if this slows down by 10%, that means this thing has to be 0.90, right? Because this would be 90%, this velocity D is basically 90% of VA. It's 10% less. So that would mean that 1 plus E divided by 2 cubed, right, is going to be equal to 0.90, right? So if that's the case, in the next video, if that's the case, that means that, what do? We take the cube root of both sides, right? We take this cube root, right? So we have 1 plus E divided by 2 is going to be equal to the cube root of this thing, 0.90, right? So we got to multiply both sides by 2 now, right? And then we'll go what? Subtract 1. So E is going to end up being cube root of 0.90, right? Times 2 minus 1. So if we find, so our E is a measurement. So if we find that velocity D prime is actually 10% less than velocity A, then we can put our V in there. And that can actually be measured. We can actually measure that with a radar gun or whatever you want to use, or laser, whatever the case may be, you can actually measure it. So that's the next video. We're going to start looking at how can we apply all these things to Newton's Cradle. And this is just one way of measuring your E. Okay, so I hope this helps you. I mean, physics is not always easy. There's a lot of math, there's a lot of garbage, a lot of other good stuff, but hang in there and I will do the second video on Newton's Cradle. I hope you subscribe and I hope you like it. Thank you.